Hello, we're going to take a look at another logistic problem. This one we're looking at data from cable TV. We have a table that shows the number of cable TV subscribers in millions, and that is subscribers to basic cable. So we have the years here starting at 0 and going up by 5s, and how many million subscribers. The first thing we're asked to do is find a logistics model for the data. We don't do that by hand, but with the help of our calculator. So let's head to our calculator. My first step on my calculator is to put the data in, so I hit Stat and Edit, and I did take the liberty of doing that before I started the recording so we see the data. So my next thing to do is go to Stat, over to Calculate, and I want to find Logistic in this list, so I'm scrolling down through this list looking for Logistic. And it is option B, so I'll hit Enter. I do want to store this equation so that I can do different graphing things with it. So at Store Regression, I'll hit the vars button, arrow over to yvars, choose Function, and choose y1. Enter a couple more times, and then keep in mind that this always takes a minute for your calculator to do it, even here on the computer. So they have my formula. The 69.78 is the top number, which goes up here, which is the limiting value. The A value is filled in here, and the B value is part of the exponent. So going back to my PowerPoint slide, find the logistic model. So C, the number of cable subscribers, is equal to 69.78 over 1 plus 7.075 e to the negative 0.194, and then year is our x. Then they asked me, by what annual percentage would you expect the number of cable subscribers to grow in the absence of limiting factors? So this absence of limiting factors is talking about the beginning of the logistic curve. So we did not graph this yet, but because it's logistic, we expect a curve like this. This first half of the curve up to the point of inflection is an exponential curve. And so we can find the intrinsic exponential growth rate for this. So off to the side here I have my formula, which my calculator then gave me, so I don't need to do that. I have how to figure out B, which I already know. And then I have the formulas relating A and the percent and the R. So what I see here is if I can figure out A, then I can separate the 1 and have the percent. So in order to figure out A, I need to take e to the r power. Notice that the exponent here is not negative. All right. So what I do is I have A is equal to e, and my exponent is 0.194. So I'm taking this directly out of my formula. Here's my e. Here's my 0.194. I don't use the negative because in this formula it does not have a negative r. And so I type that into my calculator and write that value down, and I have 1.214. So this is A is 1.214. When I look at A is a combination of 1 and the percent. So if I subtract 1, I have 0.214. Multiply that by 100 to change it from decimal to percent. And so I have 21.4%. All right. So if there was no limit on the world population, nobody had financial constraints, there were no other services around, cable subscribers would go up each year by 21.4%. And that's what starts at the beginning. But there are limiting factors. There is a limit to the people who have access to cable. There's a limit to what people are willing to spend on cable, and there's lots of other services. So it does not continue, it starts to level off. Next question asks us, what is the maximum number of cable subscribers? And for this, we just need to look at our formula. We know K in the formula, the number on the top, is the maximum. And so we'd have 69.78 million from the context of the problem. Next, it asks me, when is the number of cable subscribers growing the fastest? So for this, I have to remember that fastest is a hint to find that point of inflection, because that is where it switches from growing at an increasing rate to growing at a decreasing rate. We also know that the point of inflection is half of the maximum capacity or limiting value. So half of K, which would be half of 69.78, and again, going to my calculator for that number, 34.89. So that's how many is half, but we want to know when it occurs. So we need to go out to our calculator and solve this by graphing. So in my calculator, I'm going to y equals. I did store this equation earlier. If I had not stored it, I would need to type it. And then this y2 is where I want to put this amount that will be part of the point of inflection. So 34.89 is half of the limiting value. Then I want to set up my window. So in my original data, the years were going up by 5, and the years went up to 25. So I'm going to pick to go twice that far, out to 50. And that's just a pick number, and I don't know exactly, but I'm hoping to capture like the full logistic curve. And I know from my formula, so let's do this first, 0 to 50, what the limiting value is from my formula. So back to that thought. And that was at 69.78. So I'm going to go a little bit higher than that and go up to 70. And so my graph, I'm expecting a logistic curve coming up against the top of my window. And I have that. So here's my curve. This red line goes through my point of inflection. And I want to find that point exactly. So second trace, intersect, first curve, second curve, guess. And so that's going to happen in about 10 years. So going back here, this happens. So if I sketch this out, we went 0 to 50 years. And this we went up to 70 million. And we had our logistic curve come up and level off. We have our line coming through, and we get this point right here was approximately 10, 34.89. So 10 years after this started, they would be at that fastest growth point. And so 1975 plus 10 equals 1985. We saw that that actually was really close to this ordered pair, which we can see 35.4 versus 34.89, really close right in here. So this is when there was this huge jump from 17.5 to 35 and another huge jump up to 50. Okay? So that's that fastest growth. Next thing we're asked to do is estimate the number of subscribers in 2005. So I have to figure out 2005. How many years later is that? So minus 1975. And I get that that was 30 years later. And I'm going to plug that 30 years in for my x, because my x is my time. All right? So I'm going to go out to my calculator to work on that. So we said the 30 is an x value, And our calculator lets us look that up right here on the graph. So second, trace, we want a value, and we want 30. And so there it is, prediction of 68.36. Okay. This is easier in my mind than typing the formula and typing in 30 for the x, because we already had the formula stored in our y equals and we already had the graph. We could have also used our table to calculate this, so we have 68.36. So our model predicts 68.36%. And so how does that compare with the actual 2005 data? Well, in 2005, there were 65.3 million, so our estimate is a bit high. And we have something going on that our model does not account for. So in this, if we continued 2005, the actual data went down to 65.3. And when we look at the logistic curve, it levels off, but it doesn't go back down. So what is happening here is things like Netflix introduced competition. And so our logistic model may not actually capture the trend moving forward, because my guess is that moving forward, and I'll get a different color pen here to symbolize that, moving forward, instead of staying level, let me try again here, there we go, instead of staying level, that this is actually going to curve back down. This is my guess of what would happen in the future. When we have this curve back down, we're dealing with a whole different curve rather than a logistic model, because now instead of just Netflix, there's all kinds of different competition to cable.